brief agenda. So I'll be talking about world computer and the scaling laws and a few other things like data center electricity demand, because as the demand for AI is increasing, so is the demand for electricity. And then Azure infrastructure, brief introduction about it, what are the basic building blocks, and then about few infrastructure innovations that are currently going on in the industry. AI agents, I think a lot has been talked about this, so I'll probably skip this session. And then evolution of AI models. The reason I want to cover AI model evolution is just to briefly touch upon that, why do we really need GPUs to run these models? And the next one is about, applications, few applications that we're using, and key takeaways. Plus, if there is time for Q&A, we'll take it. Otherwise, I'll be around the lunch table. And please feel free to grab me, and my colleague Shalendra was sitting here, so we'll be more than happy to interact with you. So here we go. So at Microsoft, we think of Azure as building world's largest computer or AI computer. So if you look here, we have presence around 70 plus Azure regions. So when we say region means like it can have multiple data centers in it. So I'll just take an example of our Dublin region. So Dublin, we have about 2 million square feet of data center capacity. And just to put that in perspective, that is as good as or as big as 35 American football fields. So that's just one region in Dublin. And then we have about 400 data centers globally across the world. And then there is about 600 kilometers of optical fiber, which is needed to interconnect all these data centers. So that is good enough to go around the earth 15 times. And we have presence in about 190 metro stations. So isn't it really challenging? So as Mr. Manish Gupta put out, right, so we are really in the middle of an era where we are building the most promising and the most complex computers of our generation. So here's a brief insight into the data center that we have. So we have in Wisconsin, Atlanta, and these are completely liquid cooled data centers of Microsoft. And whatever you see below New Zealand, Belgium, Malaysia, they're all air cooled or mix of this. And certainly you don't see India here, but we do have data centers in India as well, in Pune, Chennai, and Hyderabad. So as we see this, right, so as the world is changing, it's really changing very fast. And it's changing in three fundamental ways. So I'll cover that in the form of 3 slides. So first thing is about scaling laws, right? So a lot of people, a lot of keynote speakers, they talked about Moore's law, which stated that the number of transistors per microchip will double every 2 years, right? But if you look at AI, the AI law scale says is the AI performance and AI capability will double every 6 months. Isn't it amazing? So that's the reason like we see a lot of traction happening in AI over the past 3-4 years. And it's evident from the facts that there's a recent report which was published by Morgan Stanley. It says that the 4 biggies or 4 biggest hyperscalers, which include Microsoft, Amazon, Meta, and Google, would invest about $300 billion in 2025. So we are towards the end of 2025. So this report should be out, and I think we are very close to this much of spending AI infrastructure. And this is going to grow. It's going to grow to over $350 billion in 2026. And if you go all the way through 2030, it's supposed to touch about $2 trillion plus. So isn't it amazing? Like it's a huge investment which is happening. So this is the first fundamental shift which is happening is like the infrastructure growth. And the second thing is as this infrastructure is increasing, so is the demand for electricity. Right? So this and every rack needs a good amount of power, right? It's not like few kilowatts, but it goes up to let's say 125 kilowatts. And as we are innovating, it's going to the order of megawatt. So what this law or what this curve says is between 2022 to 2026, the global demand for electricity would increase from 1.4 to x. So just to put it in perspective, right? So that means like it is as good as adding a country like Germany or Sweden into the global consumption. And then the third one, or third fundamental shift, if global crime, right? If crime was a world economy, right? It would have been right after US and China, cybercrime. Isn't it amazing, right? So there's a lot of spend which is happening on the cybercrime right now, right? So it is be it in the form of like how to prevent this, or people are getting young crime. So, and if you look at this, it says that by 2026, the amount of money that will be spent on cybercrime would be of the order of 11 trillion. So, which is just after the economy of US and China. So, as we move along, right? So, if, so what we learned so far, so there are three key takeaways, right? So, first one is the law of scaling, or AI. I mean, the law of AI scaling. Number two is demand for global electricity, and the number three is cybercrime. And if there's another key takeaway from this presentation today is that is like way we think about designing a data center, our approach has to change. You know, the boundaries between silicon, if you look at a data center, what it comprises of silicon. There is an underlying hardware, software, and there are servers. They're put into racks, multiple racks working with each other. We need switches to connect everything, right? So the boundaries, the traditional boundaries between all these elements have to blur. So what it means is we cannot think of silicon being done by one person and then like server done by another person, right? So all these things have to be co-designed and co-optimized. And that's what has been Microsoft's approach so far whenever we think of designing a data center. And this is some of the key elements of a purpose-built Azure infrastructure. So what we have here is, we have compute, or which is Cobalt, is a Microsoft silicon, or we call it as first-party silicon. So this is our 64-bit ARM Neoverse architecture. And this is the way this Cobalt chip itself is designed. It is designed in such a way that it can interact with the rest of the elements in the Azure network seamlessly. And the next one is our AI solution, which is Maya. So many of you would have heard about Maya. So Maya stands for Microsoft AI Accelerator. So if we look at this, this is also designed with a system approach in mind. What that means is, like, because to power or cool these high powered GPUs, right? So we need a good amount of cooling. So they cannot be simply cooled with the air-cooled solution. So they have to be liquid cooled. So how do we transfer the heat from this component top using liquid cooling and then take it out? And then how do we cool the liquid using hot liquid, which takes the energy out, and then like bring back the colder liquid? So when we say that we are designing silicon, so we are designing silicon keeping the system approach in mind. And then we have Azure Boost DPU. DPU stands for data processing unit. So traditionally, if you look at a lot of these virtual functions or other functions like network, security, storage, they were done in a CPU, and which used to consume a lot of CPU core bandwidth. And that's where like CPU bandwidth is consumed for doing these basic functions. We can it impacted revenue, right? So that's where this Azure Boost DPU is designed. So it takes care of virtualization functions and the basic networking, storage, security function. It takes care of offloading that. And then corresponding to this, we have Azure Boost Management, which is an underlying software which works on this. And next one is security. It's about integrated HSM. So probably I'll talk about this, touch upon this in my next slides. So just summing up, so we have a complete offering of solutions from Microsoft, what we call as Agentic. So the CPU, we discussed about Cobalt 100, 200 is our CPU series. GPU is our Maya series, and then DPU is our data processing Azure Boost DPU. As we know, as everyone knows, right, Microsoft offers services to customers, right? So different customers, they have different requirements. So some customers, they have their workloads or applications which are really working well on Intel or AMD or NVIDIA. So we work very closely with our partners ecosystem. So this is our partner ecosystem, primarily Intel, AMD, and NVIDIA. And we work closely with them to have their systems into our Azure network. And so that we can serve the numerous or wide variety of customers. Yes, I think I'll spend some time over here because this is something really a system approach, right? So when we think about data center, what is a data center? What it comprises of? So this is one example of my Microsoft AI Rack, which is available publicly. So just think of it like what goes into a data center, right? What we see is a rack. What is needed is we talk about GPU. So GPU is a silicon, right? So we need silicon, right? And then we need power. So going chronological in a order. So in order to have a rack, we need to power on different servers which are available in the rack. So what is needed is a power shelf first of all, right? So which will distribute power to all the elements. And power, as I discussed, as I mentioned earlier, it goes from somewhere around 100 of kilowatt all the way up to 500. It will reach probably 1 megawatt of power per rack. And then once we have a rack, we need to manage the rack, right? So we need a rack management software. So how do we take care of the rack management? So that's where we have on the top rack management and the management network switch. So then we have AI compute nodes. So it's not just GPUs, they work alone. So GPUs and CPUs work in tandem to run any workload. So then we have different trays, so which are for your AI compute nodes, which will host CPUs and GPUs. So they are the next one. And then these elements, right, so which are there in the rack, they have to get connected to the external world. How do they get connected to external world is, or before they even get connected to external world, they have to get connected to the Microsoft Azure network, right? So what we need is a front-end network switches, so that they get connected to the Microsoft Azure network. And now we have so many GPUs, right? So we talk about 8 GPUs, 16 GPUs, 32 GPUs, 144 GPUs per rack. So how do they talk to each other? Wirelessly? No, because they are really running at very high speed, right? So we really need these GPUs to talk to each other. So when they talk to each other, they can talk, like within the same system. But when they have to talk to other GPUs in other systems, that's where we need something called backend network. And these are again high-speed backend network switches, so which are like each link operating at either 400 Gbps or 800 Gbps, and this is going to grow as we go along. So what we discussed all the elements, right? So silicon, which goes into our AI compute nodes, and then a rack management switch for managing the rack. Then we have front-end network switch so that we get connected to Azure host software, and then the back-end network so that different GPUs can talk to each other, and of course the power shelf at the bottom. But what is keeping all these elements in a rack cool? Right? So we don't have any like fans, right? Because they are generating its 800 watt CPU. It could be 1000 watt CPU, 1400 watt CPU. So how do we take that heat away? So on the left side, what you see is a cooling solution, right? So that is a liquid cooling solution. So which can, like what it does is, the way it works is, the heat from top of the silicon gets carried away with the liquid. It enters this liquid cooling solution, and then here we have a heat exchanger unit. So what it does is, it cools down the hot liquid and then sends the cold liquid, and that's how this entire heat gets exchanged. So that's so these are basic elements of Microsoft AI rack. And just a bit deep down into one of the server design, I'll not go into the details, but what I want to touch upon is integrated HSM. So this is nothing but, it's a hardware security module. And the third fundamental thing I talked about was cybercrime, right? So how do we keep our systems secure, right? How do we take care of the latency? Latency matters a lot. Nowadays, cybercrime happens in nanoseconds, or let's say not nanoseconds, microseconds or milliseconds, right? So how do we make our network elements, servers, so fast that those things can be tracked? So that's where we have introduced this Azure Hardware Security module. So this is nothing but what happens when a server comes up, right? So it goes through a lot of key management processes, and the keys are everywhere, right? So while it is going through key management processes, right? So what happens traditionally, all these keys are stored in a large bulky server somewhere in a geographically located location, right? So which is far off. So keys have to transfer, or let's say traverse all the way from this server to the central management unit and then come back. So it introduces a lot of latency, right? So how to avoid that? So introduce this integrated HSM, which gets into every server. So that after power on, the keys once are fetched from the central server, and then afterwards, for any key management process, so all the keys are taken from the local server, which reduces latency and it leads to performance improvement. And one more thing just want to touch upon is Calyptra. I'll not go over each and every network element here. Calyptra is a Microsoft, Microsoft is working with our partners to define a root of trust IP. It's not like malware which is entering into the system. So that's where Calyptra has been designed by Microsoft, and it's an open IP. And then Microsoft expects that all our vendors or partners who are supplying us components, they also use this IP into their components so that attestation, authentication is taken care of. Problem, right? So GPU, number of GPUs per rack are increasing. So we had about 8 GPUs earlier. It's increased to 36. It has become 72. Work is in process for maybe 144, and then so on and so forth. Electricity is one, and the second part of the problem is cooling, right? How do we cool this entire heat producing rack? So this is one of the innovation in the world of cooling, right? So if you look at traditional data centers, so they are not liquid cooled. So what they are cooled, so they are air cooled, right? So if we have to introduce liquid cooling in an existing data center, how do we do that, right? So that's where this solution is coming. So this is what we call this, this is a cooling at higher voltage. I just briefly discussed about this earlier, and then this is it can be deployed in air cooled facilities. And this is another innovation which is happening in the power infrastructure, right? So what we do typically with power, we take the AC and then convert that AC into DC, generate power. But these methods, there are a lot of losses which happen in the process, right? So how do we make sure that we are more efficient, right? So that's where solid state transformers are being discussed, or there is a lot of innovation happening. Microsoft is working with our partners to Meta, including Meta, to work on these areas. But at the same time, if the power requirement for a rack is so high, it is 300 kilowatt, 400 kilowatt, half of the space will be taken up by the power itself in the rack, so which is deploying, right? So do we need to have more GPUs in a rack or more power? So that's why we are moving towards a disaggregated power architecture also. So in the sense, like, we will have racks which will generate power separately, and then one rack will feed to one or multiple of AI racks. Okay, so far with me. All right. So this is it's about the difference between. So I was having a discussion with some of my team members, and then we said that we need to invest time in patenting, and then innovating, right? So we decided that, okay, let's go for it the next day. So now before getting into that, right? So I wanted to prepare a small presentation, right? So typically, if I had gone the traditional way, I would have framed the agenda, and then you asked some of my colleagues for help. You do this slide, you do this slide, and then we get into the presentation. So no, I didn't do that. So what I did, I opened Microsoft M365 Copilot. And as I'm thinking, as I'm framing my agenda in my mind, I wrote all my agenda points in the chat window. And then I also told Copilot that I have this in mind, and I want to run these sessions over the next 4 weeks, 4 hours each. Practical example, right? And at the same time, give me, I need to keep my team motivated about this, right? So this, and should be fun activity, should not be a burdensome activity. So I spent about 5 minutes writing a prompt, and within 10 minutes, I got a presentation with awesome pictures, more apt for the presentation, and then I had to work for maybe 10 more minutes in fine tuning, and it's done. So what it says is industry. The key message is the industry is moving to a newer way of working. Isn't it? Continuous change is the norm, and if we don't learn, we'll remain behind. And certainly, it is a time that we use AI agents or AI, colleagues, right, as we call it, to be proactive in our environment. right? I'll just skip this slide. This is boring? Okay, I thought you said absolutely boring. Yeah, sure. Yeah. So accelerating agentic AI, right? So far we discussed about, like you have heard a lot about agentic AI, right? So how do we make this agentic AI run on this infrastructure? They look like two disconnected pieces, right? So there is the infrastructure, we talk about agentic AI models, chat GPT, but how these two things, they marry to each other, right? So how they work. So this, I'll briefly touch upon that. I know time is really short. It's very difficult to cover so many things in such a short time, so I'm just running through. But I'll be happy to discuss more details after this meeting. So evolution of models, right? If you look at, there were so many conversations around large language models, right? So these LLMs, right, so they've scaled beyond trillion parameter mark. If you look at chat GPT, right, so we're talking about 2 trillion to 5 trillion parameters for chat GPT, right? So it's increasing, right? So these rapid advancements, right, it's really, really fast, right? And we look at this LLM, they're finding application in agentic AI, right? So in terms of agentic AI, a multi-agent system, right? So which is capable of planning, coordinating, and performing tasks autonomously, right? So these are the things which are being done by agentic AI. So likewise, this LLM, they're finding their penetration into the enterprise workflows as well. So Microsoft, we use like agentic AI left and right. So just to put another perspective, right? I think there was a post by Satya Nadella, right? So SDLC is a software development lifecycle. So there are teams that are working on creating a multi-agent system which will automate complete software development lifecycle. Right? So this is finding application enterprise as well. So where teams are using, so personally we are using it for requirement capture or like identifying duplicate bugs, coding, and optimizing our test scenarios, so on and so forth. So, and in order to build these models, right, run these models, what we call as GPT-5 or these big models, right? So where are they running? So we say they are running on GPUs. And where are those GPUs? In the racks that we saw. And where are the racks, right? So one rack can have a max of, let's say, as on date, 72 GPUs, right? But we say that a chat GPT model is running on thousands of GPUs. So that means these racks are also talking to each other in the form of clusters. And those clusters are talking to each other again. So that's how it scales. And whenever we do a data center design, scaling or scalability is always on top of mind for us. So now let's say we have the infrastructure, right? And these models are so big. So how do we run these models onto this infrastructure? So there are two techniques, very basic techniques. One is a parallelism and the other is collectives. I'm not sure if you've heard of that, but I think most of you would have heard about that. So parallelism and collectives are the backbones for this. So what is parallelism? So this is, you can just view it as, view this as, let's say, multiple GPUs working in parallel, right? So there are three techniques which are used. One is a data parallelism, then there's a pipeline parallelism, and then there's a tensor parallelism. So data parallelism, right? So what it does is, like, the entire workload is split into multiple GPUs, or every GPU has a replica of the model running on it, right? So that is data parallelism. So certainly this approach has a flaw because the model size spans across multiple GPUs, cannot run on a single GPU, right? So that's where, like, this is the con of this, but if the model size is small enough, which can run on GPU, this approach is followed. So likewise, pipeline parallelism. So this is, if you look at the concept, right, so concepts are very similar to whatever has been there in the industry for a long time. If you look at a manufacturing flow, right, so what do we do there? We split the task, because in manufacturing, when you go to manufacturing flow, right, intent is we should make use of every second, every minute, every hour effectively, and they should never sleep. Yeah. So what we are doing here is we are slicing and dicing the larger model into pipelines, and each GPU is catering to one or multiple of these pipelines. So if we compare this to the assembly line, so let's say the assembly floor needs about 7 steps. So first and second step can be fed to GPU 1, step 3, 4, 5 can be fed to GPU 2, and then rest to GPU 3. So that's how this works. And the third one is tensor parallelism, right? So one simple example I give here is, if let's say there's a large matrix multiplication, right? So that can be broken down into smaller functions, and each of the matrix multiplication function can be fed to GPU. So now what we have done as part of this process parallelism, we have split the work, right? So each GPU has done the work, but now someone has to get the work back, synchronize it, and produce the outcome, right? So that's where collectives come into picture. So parallelism is one half of the story, and collectives form other half of the story. I'll not deep dive into collectives, but like parallelism, as we discussed, it's about splitting the data and the tasks. But when we have to collect the data, right? So that's the outcome. So that's where collectives come into picture. And there are certain approaches like all reduce, all gather, so on and so forth, reduce, scatter, all to all, or broadcast, right? So these are different techniques which are used in collectives. And this is just basically one example which shows that how the matrix multiplication can be done. It can be done in 2 ways, and this is how it shows that all reduce. The first picture you see on the top is when it does all reduce manner, and the bottom one is when it does all gather manner. Okay, so I'm very close to the end of my presentation, so please bear with me for maybe 2-3 minutes. Yeah. Okay, so M365 Copilot, right? So I talked about one application previously, right? So how I got a presentation. So M365 Copilot also comes with a researcher. So I want to do a research that what are the industry tools which are available to characterize DDR5. Okay, so that's the one research I want to do, so that I can benchmark my test plan as per the industry standard, right? So I fed this problem statement to researcher. Researcher takes time. It took almost 15-20 minutes, and gave me wonderful data with proper comparisons, and then what could be apt for my research. So this is really another example that we use this researcher very effectively. So without getting deeper, M365 Copilot is an agentic orchestrator. The reason I want to bring it up is because it is an agentic orchestrator, or it's an application built on agentic AI. And this uses not just one LLM, but it uses a multi-LLM approach. So it uses GPT-5 as well as it uses as well as part of the solution. So it plans, executes, and self-checks and multi-step work across Microsoft 365 applications. And it seamlessly integrates the work across all Microsoft applications. If we look at Microsoft Office, what do we get? We start with Word, Excel, PowerPoint presentation, and then we have Outlook, and then we have Teams. So personally, I will give one very simple example which you can try out. Right? So I just gave an idea that I want to open a startup in Bangalore in this domain. And I fed that problem statement to M365 Copilot. So I got what is needed. I asked what are the steps needed to do this. And then first I gave it in India, so it gave me the process, and then I said in Bangalore, so it gave me all the steps that what you need to do, where you need to register. And the next step was, okay, so now having done that, so can I get to the next level that can I put this idea, or can you elaborate more on this idea, and give me a 2-page Word document. And I really got a wonderful document as part of that. And the next thing is, if the idea is there, I have more details into that. I want to put into presentation so that I can go to VCs for funding requirements. And I fed that requirement in 365, and I got a fantastic presentation. Just you can imagine that all these tools are seamlessly integrated into M365 Copilot. And the moment I got a presentation, I just prompted it. Okay, so I know, let's say admin. So I said, admin, I just put her name, not the email ID. Please go ahead and schedule a meeting with so and so person, no mail IDs, and then asking time for a meeting which should, where his calendar is freed up. and really it helped me in writing an email, and in fact, like it created a complete invite. Only thing it didn't do is sending the invite, because that is something which has to be done manually. But everything done in half an hour. So these are really very good practical examples of M365 Copilot. I mean, for people in management, so they are very effectively used by people who are in marketing, sales activities. But on the other hand, if you look at researcher, so right, so that's really very helpful for people who want to gather the scattered data in a short span of time. And then there is something about Azure Copilot, right? So I just talked about M365 Copilot, right? So which is seamlessly integrating all the Microsoft Office applications. So Azure Copilot means it is targeted for Azure. And just three things: experience and full lifecycle agents, and then governance. I'll touch on that. So here is Azure Copilot experience, right? So this is like any normal chat. So that is the experience that we get. So this is relevant for the people who are using Azure. And then right agent at the right time. So already comes up with a concrete, or let's say a good number of AI agents, and users can pick and choose what agent is suitable for their requirement. And the third thing is about unified operations center. So this is something like you can see more results in a unified manner at a common place. So the next interesting thing about Azure Copilot is this. So Azure Copilot comes with several agents, or it's an agentic AI solution. So it provides full life cycle agents. We touched upon earlier when SDLC, or software development life cycle, can be done by agentic AI, right? So a lot of thought comes to a lot of people's mind that, oh, my job is taken away by agentic AI, right? Because software development is completely done by AI. What is it for me? No, but because there is a lot of development, right, which will still, or let's say, as far as